So we work on wireframe modeling. Then the next slide that we have to complete is the classification of wireframe entities. Curve entities are divided into two categories: analytical curves and synthetic curves. They are very important. Um, Analytical curves, those curves up to which you have done till now, they comes under the category of analytical curve. You have learned about circles, lines, arcs, fillets, chamfer, conics, ellipse, hyperbola, and parabola. These all come under the category of analytical curve. That can be drawn with the help of some equation that are present: x square plus y square is equal to 1 for say circle or arc. So they can be drawn with the help of some equations that are available with you. Point, line, arc, they come under analytical curve. Some curves that cannot be drawn with the help of these analytical curves. Some random curve like this, say, any curve, synthetic curve, they comes under the category of synthetic. Any random shape includes various types of spline. First spline is Hermite cube spline, Bezier curve, and B-spline curve. As I have told you in the very first lecture, that this is the most difficult part of the syllabus. When you come across this synthetic curve, what is this and how to do it? This is a tedious task, particularly in this subject. Only this chapter is a difficult one. Otherwise, this syllabus is all about reading and learning it. Nothing to understand, nothing to like uh, cram or ऐसा कुछ नहीं है. You have to just read it and just understand whatever it is written. Then you will be able to solve, or you are able to attempt the final exam. This particular chapter is very tedious chapter and very difficult chapter. That is synthetic curves. Synthetic curves, you have never came across the term synthetic curves in your previous classes. This is a new topic, synthetic curves. There are three different synthetic curves: Hermite cube spline, Bezier curves, and B-spline curves. This will be discussed in next chapter when you will come across the curves, synthetic curves, a chapter based on synthetic curves. So curves are divided into two categories: analytical curves and synthetic curves. Analytical curves, those curves which you already have studied up to this. You have learned about line, arc, fillet, chamfer, conic, parabolas, hyperbolas, and all that. The new thing, that new curve that you can draw any curve, any random shape, that is synthetic curve. And these can be drawn in three different ways: Hermite cube curve, Bezier curve, and B-spline curve. Now let us discuss about 3D surface model. We have discussed about wireframe modeling, in which the surface is not visible to you, only lines are visible to you. When you are talking about surface modeling, you can see the surface, you can come across the surfaces of a particular shape, though it may be empty from inside, but this is called a surface model. Surface model is a set of features. When you take a box of cardboard, in which the packing cardboards or box, that particular box, the entity will look like a box which is empty from inside, but a box itself. The surface model consists of wireframe entities that form the basis to create the surface entity. Now, how to generate a surface? Surface will be generated once you have drawn that wireframe model. Then you will increase or create a surface out of it. They support hidden lines and surface removal algorithm to add realism to the distribution. You can delete hidden lines that are not visible from the front so that it may look good. They are widely used for shape design and representation of complex profiles such as ships, aircraft, turbine blades, aerodynamic automobile bodies, etc. Let me show you some figures then you will be getting into touch with that. What is surface model? When you're discussing about some surfaces as car, it looks like it is empty from inside, but it is generated with the help of some surfaces. Now, when I am talking about curves, this particular curve, the curve, this is not a uh, you can say it is neither a circle nor an arc. It is a curve, synthetic curve that is used to design this particular shape, this particular shape, this shape, and so on. There are a number of shapes that are not covered in circles, hyperbolas, parabolas, and all that. Sometimes we have to draw altogether different shape, different circle, or different. You can see this shape also, or very random shape. When you want to draw it on your say AutoCAD, you use an entity that is spline curve, hermetic, Hermite cubic curve, then B-spline curve and Bezier curve are used to draw such surfaces. Then you extend this surface, this line into a surface. This aeroplane is also a surface model. This ship is also surface model. They are widely used for the ship shape design and representation of complex profiles such as ship, aircraft, turbine blades, and automobile bodies. They are utilized for mass property calculation, creation of finite element mesh. As I have told you in the morning also, the surface is being divided into a number of small boxes, like the surface of this car is being divided into very, very small areas. This particular process is called mesh generation. They are utilized for mass property calculation. You can use this small areas for the calculation of stresses and mass property calculation. This particular formation of these boxes is called mesh generation. Similarly, you can see this on the airplane also. The mesh is generated on the airplane also. So this mesh is used for calculation of different types of analysis, FE analysis. NC tool path generation, checking of interference between mating parts. And you want to check the interference between two mating parts, those who are in close proximity, and you use this surface model. They require high computer time and memory in wireframe mode. Now, surface modeling requires high computer time. You need to have to devote much time than you do it for say wireframe. Yeah, extra time is required. Same when you save a particular figure that is surface model, then that requires a large space also, memory also required. So this is some of the figures that are related to this modeling or surface modeling. Then 3D modeling, 3D solid modeling. Solid modeling is the best technology solution for parametric design and manufacturing applications. The initial was wireframe model in which you join lines to form a surface. It looks like a body, but it is actually empty and it is generated from lines only. When you, instead of lines, you generate surfaces along the surface, along all the faces of the body, then that is called surface modeling. When you talk about the solid modeling, we don't consider surfaces. In this case, a complete solid is being generated on the CAD software. Right. Solid modeling is the best technology for parametric design and manufacturing. So it is also called volumetric modeling. The database of solid models contains both geometrical and topological information. To draw any diagram with 3D solid modeling, you need to give information regarding geometrical and topological information. Both are required. They support hidden lines and surface removal algorithms to add realism to the display geometry. The hidden lines that are not visible from the front, that can be removed with the help of in this solid modeling. They also support shading and rendering. Shading process is also possible in this. They are used for evaluation of mass and geometric properties like FEA, kinematic analysis, fancy tool path generation and verification. All type of stress analysis, mass and geometrical calculations, area, volume, and all that, everything you want to calculate will be, we can calculate it easily in this solid modeling. Process planning, tolerance, surface finish, features, assembling, robotic, kinematic, and dynamic checking, making tasks. This is already we have studied, so this can be done easily with the help of this solid modeling. Disadvantage is that they need large computer time and memory compared to other modeling systems. As a system, as an object looks like a solid, it requires large memory to save that in the computer. This is the biggest major disadvantage of solid modeling. Irrespective of its realism, the object looks very real when you model it in solid model. So this is all about solid 3D solid modeling. If you have any question, then in geometric modeling we have a 3SG or CREP. Sometimes in final exams or some exams also, you may be asked to explain CSG. What is CSG? Sometimes you may be asked what is CREP. Both of them means the same, constructive solid geometry. And this CSG model, object can be divided into set of primitives that can be combined to certain order following a set of rules to form an object. Some primitives, what do you think about primitive? Primitive is a random shapes that are already available in our CAD software. A cone is available, a frustum of cone is available, a cylinder is available, a wedge shape is available in some of the CAD software. Sphere is available, torus is available. These comes under the category of primitive. So what constructive solid geometry tells us that you need to combine these primitives to form a new solid using Boolean operation. What Boolean operation is, let me discuss it in next slide. First of all, you must know what is a primitive. Primitive is all these diagrams, a cone, cylinder, sphere, then pyramids, prisms, cuboids, all these shapes are available in your CAD software. You just combine these shapes to form a new shape. This process is called constructive solid geometry. Now talking about Boolean algebra, my next slide is based on that, Boolean operation. Sometimes you need to draw this type of shape, or sometimes you need to draw this type. There are two primitives. One is cuboid and another one is the cylinder.
सर
When
ये
you
कैसे सर ये समझ नहीं लग
combine
रहा
these two,
सर दोबारा दसिए
so let me explain this again. Boolean operation. What is a Boolean operation? You have a cuboid, you have a cylinder that is on your screen. When you try to join these two, that will result into this. And if you subtract cylinder from this cuboid, you will get this. A minus B will result into this. So these are Boolean operations that are done to form different shapes joining your primitive shapes. Primitive shapes are all these shapes will come in the category of primitive shapes. Again, constructive solid geometry. We are to manufacture this. We are to, or say, design this. How to draw this? How to make a product like this? You need to have this. You need to have this. If you join these two, it will form this union of and this will result into this. A cylinder, small cylinder, a cuboid. When you join it, placing over here, it will result into this. Then subtracting this cylinder from this end, that will result into this. Subtraction of this from this end, from here, will result into this. And this is the first branch of your construction process. And second is, you will have a cone and then a cylinder. If you join these two, you will have this. Or say, yeah, instead of cone, you can take a frustum of cone. Then if you join these two, that will result into this. And then after that, a cone has to be subtracted, that is eliminated from this. That will result into this. Then if you join these two, that will result into this. So for this case, we use primitive to combine with the help of Boolean operations to form a particular job related to whatever we want to draw. So let us take the first poll for today's lecture.
Okay.
Next, B-rep boundary representation. See, earlier we have done CSD, C-rep or B-rep. Boundary representation is based on the principle that any physical object can be considered to be bounded by a set of faces. It consists of vertical edges, vertices, edges, loops, handles, and faces. In boundary representation approach, a solid model is created using set of faces as shown in the picture. Each face is bounded by edges and each edge is bounded by vertices. So in this particular case, instead of uh, joining the primitive, we use faces we join faces to form a solid. Faces, when two faces join, an edge is formed. When more than two edges or faces join, it may reaches the vertices, a handle, and which faces can be formed. This is the process of forming an solid object in boundary representation. In CSD approach, we use primitive, the solid objects that are already available in CAD software. We join these solid bodies to formulate a particular product. But in this case, we use faces and then we use join these faces to form a particular solid. So this is all about this chapter. Now we will take another chapter. Welcome back. And now we are moving to third chapter of your syllabus, that is representation of curves and surfaces. So this is one of the chapter that is quite difficult irrespective of the previous one. So first of all, classification of curves. When you talk about curves, you draw curves. These are two types, analytical and synthetic curves. We have discussed this in a brief in the previous chapter also. Analytical curves, those curves that we already know how to draw them, how they actually look like. Those curves are called analytical curves. And analytical curve has some equation that you already know. So how to draw a circle? There is an equation for circle. You know how to draw a circle x plus y equal to 0 or 1. How to draw an arc, hyperbola, parabola, and ellipse. They all have a fixed formula to generate these curves. So can be represented by simple mathematical equation. Has fixed form and cannot be modified. Right? So these are called analytical curves. Synthetic curves can be described by a set of controls. Now we will be discussing what are control points in this chapter. So they can be represented with the help of some control points, have limited flexibility in shape range.
Sir, ਜਿਹੜੀ synthetic curve ਹੈ sir ਇਹਦੀ ਕੋਈ ਕੋਈ example sir ਕੁਝ ਹੈ sir?
Yes. This chapter is all about the synthetic curve. Hermite
Okay, sir.
cubic spline, Bezier curve, B-spline curve. As we move on, these are curves are going to come, right?
Okay, okay,
Uh,
okay.
don't be panicked. We will be covering all these curves in this chapter. So this is uh, this curve basically a curve on your screen. A random curve is comes under the category of Hermite cubic spline. Thus, these having two tangents at the ends, all these curves are Hermite cubic spline. Those are having tangent at the ends are called as Hermite cubic spline. Then the second one is Bezier curves. These points that P0, P1, P2, P3, we were discussing some control points should be there. So these are the
हाँ जी, हाँ
control
जी.
points of this curve. This curve comes under the category of Bezier curve is a synthetic curve. So this is the equation that is going to be used to draw these curves, right? So these are some of the Bezier curves. Again, you can draw random shapes with the help of some curve. Now this one is a Bezier, a B-spline curve. Very important and very flexible curve. You can draw curve
ये
like
सर
this. You
3D
can
में
draw
बनती होगी.
curve like this. You can draw curve like this. Yes,
ये 3D वाली होगी ना, ये 3D च बनती होगी.
yes. It is drawn in 2D and 3D both.
Both.
Right? This is a B-spline curve. Right? This is going to we are going to discuss these curves in the step. We have started with this. So be patient and keep on asking me questions. Then only you can understand what is a synthetic curve and a B-spline curve. So this is about the introduction about this synthetic and analytical curve. So synthetic curves are further of three types: Hermite cube spline, cubic spline, Bezier curve, and B-spline curve. Three curves that are in your syllabus. Only these curves exist only, right? Book if you want to read about. Let me pause this and give some curvature continuity. Sometimes we want to join two different curves. Two different curves are to be joined. So the order of continuity is how we consider it, how much close the contact is. Order of continuity is all about that. We call it a zero order parametric continuity. Zero order parametric quantity. If the two curves section must have same coordinate position at boundary point. We call it C0, the C0. Two curves are joined, but they are not smooth when they intersect, right? If they coordinate touches one another, then we call it a zero order parametric continuity. C1, first order parametric continuity. The tangent and first derivative of the two curves are equal at the joining point. The curve is different, this curve is different, red curve is different, black curve is different, but the tangent of first and second are intersecting or they are in line with each other. Then we call it is first order parametric equation or first order parametric continuity. And similarly, if a curve like looks like whether it is of two curve or single curve, the continuity is such order, then we call it second order parametric. Both the first and the second parametric derivative of the two curves section are same at the intersection. You cannot judge whether these are two curve or a single curve. Then that particular continuity is called as second order parametric continuity. I hope you have understood this. Interpolation and approximation. Interpolating curve and approximating curve, right? When the control point, where we call it a control point, P0, P1, P2, P3, and P4, these are called control points. When control points lie exactly on the curve, we call it interpolating curve. Why we call it a control point? When you have to generate a curve in AutoCAD or CAD software, you pick a line, polyline or curve, this curve, you will pick a curve, or click on the screen at some point. Then again you will click on some point. It will generate and curve automatically. If you pick that point and drop it downward, then the curve will reach here. That means the curve that is being generated is controlled by these points only. If you change the position, right? If you place your first dot here, second dot here, and instead of here, you place a dot over slightly above that, the curve will reach from this end up to this. And if you place it downward, it will come here and it will end it somewhere here. Wherever you place these points on in AutoCAD, that curve will follow those points to form a particular curve. This is called interpolating curve. When the curve is touching the point where curve has to be generated. Sometimes the approximating curves are generated in which the control point does not lie on the curve. Instead of that, it lies outside the curve. Just like see, it is lying outside, this is also lying outside, this is also lying outside. But still, if you pick or instead of placing the dot over here, if you place a dot here, the curve will automatically get a bit uh, curved more. It will get more curved at this end. If you place a dot instead of here, you place a dot somewhere below that, the curve will get slightly curved more. And if you place the curve, if you place the dot slightly above, the curve will become straighten up and so on. So this is interpolating curve and approximating curve. The difference is in interpolating curve, the dot or control point lies on the curve, and in approximating curve, the dot or the control point lies outside the curve. Right? Then there is another term related to convex hull. Convex hull is which is assumed in which the curve is being enclosed. The dots in which the curve is being enclosed is called convex hull. Convex hull property ensures that a parametric curve will never pass outside of the convex hull formed by the four control vertices. Right? If you draw it, there is a four control point, and if you join these points, this forms a convex hull. The curve will almost cover inside it. And this is interpolating line, the left hand side interpolating as the curve is passing through its all the dots. And the second one is approximating line in which the dots are outside but the curve is inside and it is not touching any of the dots. So this is convex hull. Now, parametric and non-parametric equations. We are now to discuss about these parametric equation and non-parametric equation. What are non-parametric and parametric equations? We will discuss parametric and non-parametric equations. Why we are studying parametric and non-parametric equations? Because curves that we generate, they are based on some equations. So that can be parametric equations, that can be non-parametric equations. So we will study first what is parametric equations and non-parametric equations. Then we will move on to the equations of the curve. Explicit non-parametric equations. The non-parametric equations are further of two types, explicit and implicit. Now, it is pure mathematics. You must be very much aware about this. Let me explain you what is this expression all about. In explicit, when a P point has three x, y, and z coordinates, say x, y, and z coordinates. A P is a point, it has x, y, and z coordinates. X is a function of x. X is a function of x. Y is again a function of x. That means when x will change, y will also change accordingly. Z is again a function of x. What is the meaning of this? The values of x, y, and z, the three coordinates of a point P. Y will be dependent on x. X is already dependent on x. X is written as x. X means x is directly dependent on x. If if the value of x increases, x is going to increase. Similarly, the value of y is also dependent on x. If the value of x increases, y will automatically increase. Y is a function of x. Similarly, z is a function of x. That can be x square or 3x, 4x, whatever can, according to equation. But in explicit equation, the point P, two of the parameters or two of the coordinates will be dependent on the third one. Two of the coordinates will be separately dependent on the third one. Now let us read this. For an explicit non-parametric curve, the coordinate y and z of a point on the curve are expressed as two separate functions of the third coordinate x as the independent variable. So x will be independent and y and z will be dependent on x. Y is a function of x and z is a function of x. So equation y is equal to c1, c2x, c3x here and c4x here. There is a unique single value of dependent variables for each value of independent variable. Now, explicit, I think is clear to you that when two of the coordinate of a particular point on a curve are dependent on the third coordinate x, then we call it is an explicit non-parametric curve or equation. Then what is an implicit non-parametric equation? For an implicit non-parametric equation, the coordinate x, y, and z are related together by two functions. In previous one, y and z are dependent on x. X is an independent variable, y is dependent on x, z is dependent on x. In this case, x, y, and z, both these are dependent on any of the two variables, not single one variable, any of the two variables. They may be related with x minus x, y minus y, and so on. Any of the two variables. X, y, and z are dependent on any of the two variables. In this equation, no distinction is made between the dependent and independent variables. Like these can be any of these, y and z, z and x, or x and y, any of the two variables, x, y, and z coordinates of any of the point P will be dependent on either x minus x, y minus c, and so on. It depends on it. So this is all about non-parametric equation. If you have some questions. Next is parametric equation. When you talk about this parametric equation and non-parametric equation, you can see that x is a function of y is a function of x, z is a function of x in explicit. And in implicit, x, y, z are a function of x, y, and yz or zx. It can be any two variables. Now, in case of parametric equation, x, y, and z are altogether dependent on the fourth variable, u. Right? They are not dependent on x, they are not dependent on y, they are not dependent on z. Instead of this, x, y, and z are dependent on u, the fourth variable. Here, curve coordinates are defined in terms of single variable called as parametric variable u. If a u is a parametric variable, then parametric form of curve is represented by defining the function to define x, y, and z independently. X is a function of u, y is a function of u, z is a function of u, where u is minimum to maximum value. If you map a real value u in closed intervals usually taken as 0 parametric equation allow great versatility in constructing space curves that are multivariate and easily manipulated. I will be showing you a simple curve. If you draw it in a non-parametric curve as a non-parametric equation, by drawing it in non-parametric equation, and if you draw it in parametric equation, what is the difference? You will see it in the next slide. So a circle, the formula for circle is x square plus y square equal to 1, and you can represent it in parametric equation. X is equal to alpha of theta, y is equal to alpha sine theta. Altogether different coordinates or different. Uh, now in first one, y is a function of x only. Y is dependent on x, so that's why we have used this. Now in this case, x and y are dependent on r and theta. Altogether third variable. You can see if you draw a curve using this formula, y is equal to under root of y 1 minus x square. You will draw this, putting this value on a curve, it will be formed like this. So though it is a equation of a circle, it is not a complete circle. Instead of this, it becomes straight at the end. Similarly, on the other hand, if you see that same number of variables are taken 1, 2, 3, 1, 2, 3, 3 readings are taken. Now the curve is much smoother than the curve generated in non-parametric equation. So poor and non-uniform definition scare you to complicate the to compute. Now better representation than non-parametric. I think it is very much clear what is non-parametric and parametric equation. Similarly, you have the equation for parabolas, hyperbolas, and circles, lines, etc. Why parametric curves? The analytical curves are insufficient to meet the requirement of mechanical parts. Why we want to draw parametric or synthetic curves? We need to draw different shapes like propeller blades, aircraft blades, rings, automobile body, ship, etc. That cannot be drawn with the help of circle lines and all. Synthetic or free-form curves solve this problem. So use synthetic curves to form this. Now let me show you some diagrams or some figures. These are the curves of a rotor of a, say, a turbine, the runner of a transistor one. This is a runner of a transistor. You can see the curves on this blade that cannot be generated with the help of, say, simple circle or a line. You have to use synthetic curves to generate such types of curves. Similarly, blades of this, and this in some shapes like this and this shape, you have to draw it on to the help of some synthetic curves. Parametric curves have fewer parameters for smooth curves. Fewer parameters makes it faster to create a curve and easier to edit an existing curve. Parametric curves are easier to animate. Now it is very easy to animate and parametric curve. All coordinates are defined independently. In this case, all coordinates are defined independently with respect to the fourth coordinate. All coordinates x, y, z are defined independently in terms of the fourth coordinate or fourth variable u. So this is why we use parametric curves, why we use synthetic curves. These are some of the diagrams that shows the use of a parametric curve. So these curves are basically of three types that we have to study: Hermite cube, Hermite cubic spline, Bezier curve, and B-spline curve. Moving on to the first curve, that is Hermite cube spline. We will try this part, first part. The Hermite cubic spline is covered today. So it is the name. It is named after the French mathematician Charles Hermite. Why we call it Hermite cube spline? It was invented by Charles Hermite. It is a synthetic curve and cubic degree which generates an interpolated curve. Why the term cubic is applied to it? As it is of cube degree and it's raised to power 3. That means why we use cubic? It is of the degree 3. This sort of curve is used to generate simple curves and is not used to generate free form curves with enhanced curve. Generally, this Hermite was the starting of a synthetic curve. When Hermite suggested this curve, it was the starting of some synthetic curve. It is a bit non flexible. It is bit not flexible as you cannot generate a random shapes with the help of it. The curve is synthesized using two extreme data points and tangents as these endpoints. So basic conditions for generating an Hermite cubic triangle. You need to have two data points, two control points, and along with that, you need to have tangents on that endpoint. Now the piecewise interpolation scheme is C1 continuum. This is Hermite cubic spline that is drawn on right hand side of this curve. Now equation that is being used is of order 3 because it is a cubic order. Now this is the equation formula I0 to 3 Ci Ui is the formula. Now putting 3 C3 U3, putting 2 C2 U2, C1 U1 plus C1, where U is the parameter and Ci are the polynomial, also called as algebraic coefficient. Right? The above equation can be written in matrix form, or you all must know what is matrices. Matrices and determinants, you all have done that. Those matrices and determinants, we have converted this equation into matrix form. I have written U3, U2, U and 1. U3, U2, U and 1 over here in the horizontal side, and C3, C2, C1 and C0 like this. If you try to multiply this, U3 with C3 becomes U3 C3, U2 C2 like this, U1 C1 to multiply like this, it will come this 1 into C1 will form this equation. So if you want to write this equation into matrix form, it will be written like this. In scalar form, this equation is written in terms of x, y, and z. If you want to write it in x, y, and z terms, want to calculate x coordinate, y coordinate, and z coordinate, that can be written as C3x u cube, C2x u square, C1x u plus C0 x. Right? Wherever we are having 3, you can attach x along it, x along it, x along it, and x along it. Either you can use y if you are using y over here. Similarly, z, you have z over here. Right? So to form x, y, and z coordinate, you can use this equation like that. Now tangent vector is given by. Now to calculate the tangent of a particular equation, we generally what we do is take the differential of that. We will be differentiating with respect to u. You should differentiate p dash u is equal to 3c3 u square 2c2 u1 c1 and 0. 3c3 u square 2c2 u plus c1. This is the equation when you differentiate this particular equation. Applying the boundary condition P0 dash at u0 and P1 and P1 dash at u equal to 1, equation 2 and 6 will give result is. Now what is to be done is, we have two equations, number 6 equation and equation number 2. What actually is this derivation is to be done as, put value equal to 0, put u equal to 0 in this equation. When you put u equal to 0, now this anything raised to power if you make it 0, this whole term will become 0, this will become 0, this will become 0. Now there is no u in this term, so this will be C naught. This is how P naught is equal to C naught comes out. Now when you put u equal to 1 in this equation, you put u equal to 1, this becomes C3, this becomes C2, this becomes C1. There is no u, this will become C naught. Now P1 is equal to C3, C2, C1, C0, right? Similarly, on dash in this equation, if you put u equal to 0, you put u equal to 0, this becomes 0, u equal to 0, this becomes 0. Now C1. Now P naught dash is equal to C1. Similarly, if you put 1 in this equation, P naught P dash 1, you put u 1 instead of u, this will become 3C3 and 2C2 plus C1. 3C3, 2C2 plus C1, this will become second term. You put u equal to 0, you will get this and this equation and this equation. Similarly, if you put u equal to 1 and this equation and this equation, you will get these terms. I hope you have understood this. So we have calculated P naught dash, P1 and P1 dash. Now similarly, if you write as you have to calculate C0, C1, C2 and C3 values from this. You have a value of C0 equal to P0. You have a value of C1 equal to P0 dash. Similarly, you have to calculate C2 and C3 values. That can be calculated just by solving these equations. You will get value of C2 also and C3 also. Putting these values in third and fourth equation. Third and fourth equation. If you put the value of C0 and C1 in this equation, you will get the value of C2 and C3 also. So P0 is equal to P0, C1 is equal to P0 dash, and C2 is equal to 3 P1 minus P0 and twice of P0 dash minus P0 dash. Similarly, C3 is equal to twice of P0 minus P1 plus P0 dash P1 dash. This is the values of C0, C1 and C2 just calculated from these values, right? On substituting the values you have calculated C0, C1, C2 and C3 in equation 2. Equation 2 is this one. You put the values of C3, C2 and C1 and C0 in this equation. After solving this, you will put these values and solving it for P0, P1 and P0 dash and P1 dash, you will get this equation. This equation is called Hermite cubic curve equation in vector form. This can be your article, complete article. You can write it up to this also. So it is considered as complete article. इसके बाद whatever is this, you have to, if you want to elaborate that, you can elaborate this also. In the matrix form, you can write it UT, unit matrix for U, then matrix H, that is 2, 3, 1. U cube, U square, U is missing from this. So what is to be right? 2 minus 3, 2 minus 3, 0, because it is U is missing. So we will place 0 over here and 1. So minus 2 U cube, U square, U is missing and without U is also missing. You can write minus 2, 3, minus 2, 3 and 0, 0. Similarly, U cube, U square and U. 1 is the value for this, -2 is the value for this, and 1 is the value of this. -1, -2, 1, and 0 for this. And u cube minus u square, 1 and -1. 1 and -1, 0, 0. So you are converting this equation into matrix form. Then P0 dash, P1 dash, P0 dash, and P1 dash. Writing this P0, P1, P0 dash, and P1 dash, like this. So we have, what we have done is, we have again split this up and written in the form of matrix. Just writing that equation into the matrix form. Now tangent vector can be written as like this. Tangent is the differential of this above equation. You take the differentiation of this, 3 to the 6 u square, 6 u square, 3 to the 6 u, 6 u. This is the differentiation of this particular equation. So you will get this equation after differentiation of this equation. So these are the some of the curves related to Hermite cubic spline. The first condition and the last condition in Hermite cubic spline is you must have 2 points and 2 tangents to draw a Hermite cubic spline. What is the condition? The condition is you must have 2 points and 2 tangents to draw a Hermite cubic spline. So this is it. Then disadvantages of cubic spline. We will do it in next class. Now I'm going to finish